Shall I go ahead and get started then?
Yes, please go ahead, Aaron.
All right. So we're doing this a little bit, hoping to do this a little bit differently in that at the end when we get to Q&A, we want to have that be a little bit more interactive, open discussion. So we'll have some questions of our own as well. So I guess what I'm saying is pay extra close attention this time because there will be a quiz at the end. So what we'll be talking about is efficiency of aggregating small messages. So some of you have been around for previous years. Some of this may seem familiar. Basically, just a little bit of background refresher stuff. I know we've all heard it a million times, but we can't just keep scaling down. So increasingly, as we go forward, we can expect that code being well performing will basically be synonymous with it being efficient with its uses of memory of system resources. And the problem that got us to this talk is that modern network hardware is heavily designed for bandwidth as it probably should be, but certain classes of applications are heavily dependent upon the performance of small message rates. And the conveyor model or library was designed to address the small message problem through efficient bulk aggregation strategies. But what we added a little while back was a strategy built on top of it that we called aggregation context, and we demonstrated it in the OpenSHMEM PGAS API. And the problem that solves is the process of actually using conveyors. It's a little bit more involved and comes with its caveats. So just a little quick overview what conveyors are for those new to the class. Conveyors are basically like two-sided stateful message queues with operations to push and pull usually fixed size messages to and from them. This is implicitly two-sided. It looks like there was a bit of a duplication there. But the states of those queues and the management of the progress on them must be carefully managed through a contract, and progress is being handled on an ad hoc basis, which we'll see in a moment. The aggregation context that we designed are built on top of them to simplify the model. And what it basically means is it's focused on completion semantics of RMA operations, such that we loosen things so that the remote completion guarantees that are normally provided are not, and you only get a guarantee that anything is done when you flush the entire context via a so-called quiet operation. And between the quiet operations, continuation of progress is internally managed by the implementation as output buffers fill, or as it deems appropriate. So just to see a bit of what this actually looks like, this is implementation of histogram, simple binning of data implemented with conveyors. And the bulk of it, after the initialization that we see of it, the bulk of the stuff we see here is in this while loop. And that's what I was getting at with the ad hoc part. So each time, not for each conveyor or each application, but each instance that you're using the conveyors, you're basically making your own ad hoc progress loop for how to actually process what's going on. And here we just see the while loop is that loop which continually tries to push as much data as it can, and then when it can't, it then tries to pull as much data that's received by it until it can't anymore, and then it just keeps doing this until everything is decided it is done pushing. Meanwhile, for the aggregation context, it's simplified enough that it basically just boils down to looking like regular RMA operations in high-level interfaces that we're used to using. You just have the loop where you're going through all your data, you issue your atomic increments, towards the context that you created, you issue the quiet, and then that's it. So one of the things that we've done recently is we wanted to see how this actually performs in uh, larger situations. And by larger, I mean that we actually perform testing up to 64 ppn on 8,000 of the frontier nodes using OpenMPI's implementation. And uh, what we're testing here is we're actually using the same code that we were looking at before, basically for histogram. Um, it's the simplest implementation that gets right to the heart of the performance. If this doesn't perform well, nothing will. Um, it's just a raw performance measure. And so we're taking a regular non-aggregated approach and comparing both the conveyor and context versions we saw previously against that base. And uh, additionally, in addition to the frontier testing we had, we wanted to see how does it look on different network architectures. So we compared against what we got previously on Iris from the HPC Advisory Council, as well as also collecting some data for ORNL's Andes. These are compared to Frontier using Slingshot 11. These were both InfiniBand networks, one with an HDR 100 and one was HDR 200. Additionally, we also wanted to test for power use to see to see if we're making the uh, gains on that power efficiency that we were hoping to get, since that's the all important thing now. And for that, we were just checking some counters that Cray provided on the system to measure directly at the node the CPU and memory power levels. And for that, instead of OpenMPI, we were using Cray OpenMX. Okay, so so I mentioned we ran up to 8,000. That is true. Uh, this is the latest versions. We upgraded the OpenSHMEM implementation. So initially we were using an older one. This is also actually using Cray OpenSHMEMX 11.7. But for this, we didn't run back up to 8,000. I promise, if we had the data, it did run, and and the scaling looks pretty much the same. It's pretty flat down, from low numbers to really high. So it does. The good news is it does scale very nicely, and in fact, Context actually managed to squeeze out even a little bit more performance over conveyors. That's a bit of a discussion for another time, but basically, we were able to be more efficient in the usage of those fixed size packets in the end than the conveyor model was, since we were basically making fewer calls into the conveyor API, and that's what that came down to. But um, we want to see, how does this compare to the other architectures. And on the left, we have the same kind of graph we were looking at before, uh, where we can see that Iris was the HDR 100 and Andes was 200. And we see that the speed up is actually decreasing as we go along the architectures. But if we look at the raw message rate, we see that while there's some differences, the big thing that we're actually really seeing is that the raw performance of the non-aggregated approach is actually been improving as well. So the gap is shrinking, but nonetheless, the gains are still, as we saw, pretty substantial. Um, Going back here, it's we're getting up to 6 to 8 times performance improvement on um, even very large scales, and this is still a very big deal. So that's great, but we want to see about the energy use. So here we're looking at the rate at which time improvements are being made compared to the rate at which energy improvement is being made. And this was tested across a few different applications. Um, just to kind of see what profiles we may see. Uh, Basically, it's worth pointing out that while there's some variances here, in all cases, both time and energy were definitively and substantially improved. It's just the rate at which they were affected was a little bit different. And we saw that the PPN count was an important factor of that. More on that in a little bit. But basically, as the PPN count increased, the balance would start shifting between the CPU and memory consumption. And that started playing a different role in the total memory use. Uh, and for clarification, the lines here above 1 are time is increasing at a faster rate than energy, and below 1 is energy is increasing faster than time, or improvements to it. So this is all nice, but how can this be so dramatically successful? So, first of all, we had the point about modern hardware and bandwidth. Yeah, we know that. But also, and this was particularly highlighted by the last slide, um, the modern general purpose CPUs are quite power hungry themselves. Using them for uh, memory intensive tasks and just packing and unpacking and processing small packets of data is very efficient use of that resource. So how we have to remember how we got here in the first place. For the network side, to remain fast but also still general, they became optimized for bulk processing. But one of the consequences is that they operated at too low of a level to be able to recognize very high level semantic opportunities um, for things like aggregation within applications. Whereas on application side, generally they would favor higher level algorithmic concerns and have very little insight in the code into any of the relevant operating parameters that they're running on. Uh, Conveyors exist to help kind of bridge that gap a bit um, by, uh, in a not always obvious way, but essentially what they're really doing is providing some of the intent of the application for what it needs and when it needs it to the message processing process itself. Uh, However, they still exist solely within the application layer, which can bring its own uh, topics of discussion or debates. So we have to wonder, can we benefit from moving any parts of them into lower levels? Uh, that's where the offload comes in. Um, so conveyors are able to maintain some of that separation concerns by specifying the standard contract I referred to before between them and the applications using them. So if there's a standard contract, um, uh, that's a key point that we think maybe we can exploit. Um, Meanwhile, aggregation context enhances even further with a fixed set of RMA semantics, and as a result, it was able to get because it was less general, with it only supported those operations and they were known what they are. We were able to then get an easy progress model with that that was well defined. So we'd like to be able to take this and make a single interface out of it by moving it in part or full to network hardware via SmartNICs, providing us with uh, persistent between application launches, or even between process boundaries or jobs. We could have a persistent aggregation service running on the node, and applications would then just offload their packet processing to that hardware. Also providing us unique opportunities to be able to do some more co-design between uh, the software design and the hardware. And we have to also, we're also kind of wondering about offload potential for going the other direction from the SmartNIC to the CPU um, for any code that's dependent upon outstanding operations. So hold on. Um, this may sound crazy what I just suggested, but what we were noting is that in simpler cases, this process as described is fine. Um, you just issue a bunch of RMA operations that you don't care about too much. You just get them back later. But in many cases, you may have something more complicated with interdependencies where you're needing to fetch some data and then immediately or soon after act upon it. And that becomes problematic. So we wanted to be able to still find a way to streamline that. So we actually already enhanced aggregation context a little further using the compiler to restructure code that has those dependencies via OpenMP style directives to request the deferred execution of dependent code, at which point the compiler can just scan those blocks, extract the code into separate callbacks, manage local stack memory and such so that it can refer to it and call it back later. And then it adds it into a separate defer queue. And then as the aggregation context could do that implicit automatic progress model, they can check the completion status of outstanding operations and execute blocks or execute ranges of the deferred of the operations in the defer queue when their dependencies have been satisfied. And what we're thinking is that these callbacks could potentially be triggered by the SmartNIC through signaling of the application. Since then we can have for the lower level side, since we want to be able to have it still be streamlined. So we're not ever waiting on everything. Every time that something's happening or that something needs to be acted upon, there's a well-defined path. You do it and you're done. It's non-blocking in the other direction, basically. And then they just keep doing things when available and only ever stopping when there's nothing left that they can do. Okay. So then what about improvements to the conveyors themselves? We want to talk about that a little bit more. And for that, if we could switch over to Shubhendra, he has some slides for part 2.
Right. I don't see the share screen button. So if you can do the same that you did with Aaron, I think that'll be great.
Aaron, are you trying to fix your slides?
We're trying to switch the presenter to Shub.
Okay. Okay.
Are you able to do that?
What's I have to if somebody else presenting, I have to promote presenter.
Yes.
So what's the name? Can you?
Yes.
Okay.
Shubhendra Singhal.
Shubhendra Singhal. Yes.
Yeah. Give me a second.
Mhm.
I just tried to promote. There we go.
Perfect. I can see the screen. Okay. Okay. Let me know if you guys can see my screen.
Yes,
So now,
okay.
okay. So now we're going to talk about the future directions of conveyors and exactly what degrades conveyors in general. So there are two open problems that we pose. One is because conveyors gives us this API or the intent of performing the communication or the aggregation. The first natural question that we ask is, does a user style of programming dictate the performance of conveyors? That is, if a user chooses to code in a particular fashion, does this eventually imply degrading the performance? And second is that we also try to manage and understand the feasibility of adaptive routing and its associated challenges, since conveyors as of now has static routing that is enabled inside. So we test these two questions using two collective operations, all reduce and one-to-all communication pattern, which are both implemented on conveyors, and conveyors internally uses OpenSHMAM. So constructing the first experiment for one-to-all, what do we do is we first try to understand the topology of conveyors. So there are three topologies that conveyors offer, which is linear, that's 1D array, mesh, which is 2D as shown in the example, and cube is 3D where you have a Z additional access of PEs. So case one, what do we do is, because it's a one-to-all operation, any one randomly selected PE sends the message to every other PE using conveyors. And what do? Is we change the order of for loops. So type 1 is where for a particular PE, I'm going to send all of my data first and then carry on to the next PE and so on and so forth. Whereas type 2 is for a particular data item, I'm going to send this data item to all the PEs first, followed by the next data item, and record the average over all the start PEs. So this is what type 1 looks like. And as I think Aaron mentioned before, that we have the hardware which can definitely utilize the high network bandwidth. This approach seems to be a bit naive, that we are sending all of the data first to a PE and then carried on to the next and so on and so forth. Since conveyor buffers are generally of a fixed size, this leads to underutilization of the network, is what a naive assumption of a user can be. So as demonstrated, the inner loop is the number of data items, outer loop is the number of Ps. Coming to type 2, the inner loop is the number of Ps and the outer loop is the data items. And we have a type 3 where we simply, as shown in the picture, considering from a point of view of PE2, that PE2 is the one which has to send the data. What it does is it first sends along the column and makes sure that all the column members have the data, followed by every of those column members trying to push their data onto the row members. So experimental setup, we try to put this on GD-based cluster with InfiniBand 100 HDR interconnect. And we have 192 gigs of memory per node and 24 cores per node, but we have tested out for 16 PEs per node. The software modules that we use is OpenMPI 4.1.4 for OpenSHMAM 1.4 version. And our experiment employs 16 PEs per node for the message size of 8 bytes. So let's look at the experiment on how do we do it and how do we perform. So type 1 and type 2 essentially performs very similar to each other. And note that the blue line, which is the type 3, is always efficient because it's forwarding only one packet along the path, along the static route path that the conveyors sort of dictate. So here we see that type 2 is essentially a bit degraded as compared to type 1. We would still like to call it similar, but essentially whatever a user could have imagined, which was the naive approach, is not exactly naive. So let's look at the second collective, which is the all reduced collective that we implement on conveyors. Case 1, it stays the same, that we have type 1 and type 2. And similar, we have a type 3 situation as well. And here's the observation for the all reduced collective. So if you see, type 3 is again performant, which yields up to 10x speed up. But if we look closely at type 1 and type 2, now type 1 starts degrading and type 2 is very efficient to the point where 1024p is exactly yield 2.6x degradation. So let me remind that this is only for 2 million elements, but we have tested out for more. And this has been a consistent pattern of degradation that we saw. Although the numbers increase a bit as we increase the number of elements and decrease as we decrease the number of elements. But in general, this particular observation leads us to one thing, that is, if you just change the order of for loops, it might be very well possible for conveyors to start yielding a degraded performance, which is not ideal. So the lessons learned: always be aware of the innermost topology of conveyors, or be as close to the topology of the innermost layer or the hardware if possible for sending a packet. We observed that both type 1 and type 2 perform similar for one-to-all, whereas all reduce is 2x efficient for type 2 as compared to type 1. So what's exactly playing inside is the cost trade-off between the network congestion plus the time spent to aggregate these packets. So in type 1, we were sending only one, to only one PE, all the data items, which is where we are not waiting for much of the aggregation time of packets. Whereas if we first try to send one data item to all the PEs, that means we are appending that one data item to all the buffers and waiting until it reaches a certain limit, in which case we are waiting for the packets to be aggregated in a more execution time, but obviously results in the better utilization of the network. Versus the ordering guarantees that are placed by the software inside, which is the quiet operation. And these two trade-offs are quite tangential in nature, which is why we see type 1 and type 2 sort of differs for the all reduced collective. So here are the open questions, which is more pertaining towards the routing sort of behavior. And as I showed in the previous slide, the trade-off that we are trying to discuss. The first point that we would like to note is many libraries such as YGM, Converse, TRAM from Chapel have adopted this topology and this n-hop mechanism of communication with 2D and 3D topology. And some of them are MPI based and some of them are BigAS based. The adaptive routing, so let's come to the adaptive routing objective function that we sort of understand. And as we looked, it's quite static as of now. So if we want to make this adaptive routing technique more suitable or more optimal, what's the trade-off space that we're dealing in is a simple objective function, which is to minimize the traffic congestion while maximizing the bandwidth utilization, which is what Converse already handles, and the number of cents that are guaranteed by a single quiet op. That is, does a quiet op guarantees two asynchronous send operations to be completed, or does it guarantee 100 of them for the same size? So this is the trade-off that we are particularly dealing with when it comes to adaptive routing. And further on, to add the complexity to this, we also have application ordering, which sort of can dictate how relaxed the routing can be and how relaxed can the receival of a packet be. So we come to the final slide of our Q&A discussions, where we would like to pose some of the questions that we have. And yeah, I think that's probably it. So we would like to open the floor for the discussion and for Q&As. So let me
Yeah,
start.
so maybe first, if anybody has any burning questions of any stuff we discussed on either side, maybe we can take that first, and meanwhile, you know, soak up what you see here, so that we can then probe you for any comments that you may have on any of these topics. Any questions?
Well, my question from UCX side, what we guys can do better for you to assist conveyor-like programming models?
Well, I don't know what your thoughts may be on this, but there's even been some sort of suggestions that maybe we might look at. It might be worth looking at what it might look like to try implementing the same strategy that we had with aggregation context as a UCP protocol level layer, and take it from there. Sort of just an open topic where that whether that may make sense or have any
Sounds to
value.
me like it's very similar to Stream API that Artemi presented before.
Mm-hmm.
By the way, I understood that currently Conveyor is implemented on top of OpenSHMEM, right?
Yes, there is actually some choice. I think it's either SHMEM or maybe it's UPC.
Yes,
You can.
It's UPC or OpenShift.
Have you considered implementing it directly on top of UCX API to avoid being tied to SHMEM quite and so on semantics?
That would definitely be something that would be very interesting to see. We haven't tried touching that particular avenue ourselves yet, mostly just because it's a bit of a hairy mess to dive into there. But I know I, for one, would love to be able to see how much improvement we may be able to get from resting ourselves from that dependency.
Also, I've considered the MPI backend rather than SHMEM.
Yeah, so the basic I've many times and a couple times during this talk referred to it as a strategy rather than an extension to a specific specification or model, because it really kind of actually is. If you were to see the source code, it's all implemented as a header. It's all like a 300 lines, 200 lines, or something absurd, and that's it. And all that it basically needs is it needs a set of operations. You have these RMA calls that you're going to cover or whatever, and your progress loop that gets called from those as you go along, and some basic boilerplate stuff in there. And so in theory, it can be applied to pretty much anything that doesn't, or at least anything that doesn't cleanly to anything that doesn't require some kind of general component. Like say you want to do this, task-based processing across the network or whatever, and you're just providing callback functions of your own, and that's the unit of work. That would be something that wouldn't translate as well to what we have here, because as I alluded to before, it is dependent upon a well-defined set of individual operations that the implementation can know the semantics of. But as long as you have that, it can be applied anywhere pretty easily.
Okay. Thanks.
Any other questions?
I just have a quick question.
Go ahead.
Go ahead, Oscar. We cannot hear you if you're trying to ask a question. Yes, please go ahead.
Maybe post it in the chat if you can't, if your mic is not working.
Yeah, maybe I can read it out if you post it in the chat.
Meanwhile, while we wait for that question to come in, do we have anyone that wants to comment on any of the co-design, moving things and to lower level hardware kind of system service topic?
Okay, Keshem is came through. Any synergies between conveyors and streaming support in UCX? Both use push-pull model. I think it's what Yossi brought up earlier, that it's very similar semantics, and new streaming interface just that was presented earlier can be essentially will have the same functionality with pull-push. So there's tons of synergy, and potentially you can use it directly.
Yes, I would agree. There's probably a lot of synergy. Probably some of the bigger differences you'll see in general with that sort of thing. I don't know in detail from not having tried to sit down and actually investigate it personally as such, but probably some of the bigger distinctions may be how things like synchronization is handled. But that could very well be something where lessons learned on one side or the other could potentially change the landscape a bit.
Yeah, agreed. And I suggest for you, Aaron, get in touch with Artemy Kovalyov from NVIDIA that presented earlier. And you guys may brainstorm and see, if you're already implementing this API to make sure that we'll address your needs in conveyors as well.
And I could actually mention on this note that as it stands right now, a lot of the synchronization and the processing of the progress in conveyors at the moment is handled mostly on the push side. And that does come up with some of its own subtle problems that we've come up with, where we might really desire to be able to have a little bit more insight into it from the pull side, but we just don't have it. It's not there in conveyors 1.0. So it is push centric.
I think another advantage when using UCX APIs directly then can take better advantage of things like adaptive routing, out of order networks, multi-rail, and so on. So because we plan to handle everything in UCX as well. And if you do like shmem quiet, it's like a big hammer that not always needed.
Yes, and one of the reasons why we've mentioned and brought up or phrased, I guess, the conveyors side of things as conveyors 2.0 is because, while conveyors is undeniably a good piece of software, when trying to really put it through heavy paces and getting real deep into the nitty gritty for this stuff and maybe going a little bit out of scope of what was originally envisioned, we have been starting to get into seeing a lot of the subtle, or in some cases even not quite so subtle, weaknesses, or differing design choices, I guess, that you can see in conveyors that we run up against that give us considerable problems. So we've, either a significant, overhaul of improving it, or to some extent, re-implementing whole chunks of it is something that we keep coming back to in discussions. It just is definitely not a consideration to be taken lightly, but there is very much a reason why we've phrased it that way, because we think that, similar to UCX itself, it's possible that maybe at some point we need to consider just kind of taking all the lessons learned and starting over to make it a little bit bigger and better than it was before.